All right, good morning. So we're moving along now with the second section in chapter 4, which is exponential decay. So yesterday we went over exponential growth, and today our objective is going to be graphing exponential decay functions and using them to model some real life situations. So yesterday we talked about exponential growth, and those models kind of go up like this. So you start out with whatever amount you have, and then it slowly increases, and then it starts to shoot up more and more. So this is kind of, with our current situation with the coronavirus, this is what they were concerned about, right? This exponential growth. Now, if we're talking about exponential decay, it's still going to be a positive function, but it's going to start out with large numbers and then slowly decrease and level out over time to basically zero. So in both of these situations, the generic model or that parent function is going to be positive. It's going to stay above the x-axis. For example, like exponential decay, if you were talking about, like if you think about decay or composition, like if you put a banana peel out in the yard or in the woods or something like that, eventually over time it's going to break down and decay, right? So you have maybe, X amount of grams of mass of that banana peel, and then over time it's going to decompose into nothing, but it's not going to become a negative banana peel, right? So it still would stay positive, but it would level out to nothing. Same thing with exponential growth. If you start out, you have to start out with something. You can't start out with a negative amount of something and expect it to grow. So, your values will all be positive. Now, these are specific, right? Exponential growth, exponential decay. But of course, when we talk about certain models, maybe not something specific and tangible like a banana peel or something like that, the numbers can be manipulated to go in other locations of the coordinate plane. So sometimes maybe you'll have something that will go down here. And a lot of these things are a little bit more abstract or theoretical, but as far as the graphing is concerned, you're still going to be able to graph those manipulations of the original parent function to maybe go into the other quadrants, or like we talked about, when you flip that a value and you make it negative, now you're talking about it reflecting on the other side of the x-axis, things like that. So while those maybe don't have as many realistic applications as we think of them with regard to money or tangible or physical objects, they can still be graphed like theoretically. So we can still graph them and all that, but it's not going to be as applicable to like our real life problems that we'll do at the end of the section. So basically, when we talk about identifying or looking at the different functions here, like numbers 1, 2, and 3, we want to be able to determine, are they exponential growth, are they exponential decay, or are they some other type of exponential function? So the first thing that we had talked about yesterday was when we're talking about exponential growth or decay, you had to have an a value that was greater than 0. So in both situations, you have to start out with something, right? So if that a value is greater than 0, and you're talking about like the banana peel, for example, you have, maybe the mass of the banana peel you're starting out with or something like that. So you have to start with something, right? Now, same thing for growth. If you want to invest your money and hopefully, it grows, you have to start out with some amount of money. You can't start out with nothing. So in both situations, growth and decay, you have to have an a value of something greater than 0. Even if it's very small, but it has to be greater than 0. Now, the b value is the part that determines if it's growth or decay then. So they both have an a greater than 0, but then the b value, when it's greater than 1, it's growth, but when it's less than 1, it's going to be decay, but it still has to be a positive. So again, this form here is going to be the same for growth and decay. The difference is the b value. So when the b value is greater than 1, it becomes a growth factor. And when the b value is a number less than 1, it becomes a decay factor. And if you had a negative in there, obviously that would not be exponential growth or decay. And if your a value is negative, that also would not be exponential growth or decay. We're just going to say it's neither. Okay, so moving on to the examples. So tell whether the function represents exponential growth, decay, or neither. So the first thing we're going to do is we're going to look at the A value, right? So if the A value is positive, right, we know it could be growth or decay, but it's going to depend on this B value. So here my B is 2/7, and that is less than 1. So it's a positive number, but it's less than 1. So this would be decay. So now we go to example 2. So again, we have a positive A value, so it's going to be either growth or decay. So then we're going to look at the B value, and this time my B is 4/3. Now 4/3 is actually greater than 1. So that would be a growth factor, making this an exponential growth function. Okay, now we go to number 3, the A value is a negative, so this is neither exponential growth or decay. It's just another exponential function, but it's not growth or decay. Okay, number 4. Now, number 4, when we look at the A value, we see that there's a 10 there, which is a positive number, so this could be exponential growth or decay. However, we have this negative X value here. So let's go back and think about our exponents for a minute. So if I rewrite this, how can I rewrite this to make that X positive? Well, if you remember, when you take something and you flip it, right, then that exponent becomes positive. So that's really 10 times 1/2 to the X power. So now the A value is still positive, so we still know it's growth or decay, but this B value here is less than 1, which would make this a decay function. Okay, so now let's take a look at number 5. So number 5, our A value is negative. So as soon as you see that negative A value, you know that this is neither growth or decay, so you really don't have to take it any further than that. When you go to number 6, this is a positive A value, so you know it will be either growth or decay, so you have to focus on that factor. My B is a decay factor this time because 3/5, oh wait a second, missed something, right? So before we do that, sorry about that, whoops. What happened here? Sorry about that. Okay, so again, we have this negative X here, so we have to get rid of that negative X. So we have 8 equals, and then if I flip my 3/5 into 5/3, now that X is positive. Okay, so that changes what we were initially about to say. So again, my A value is positive, so it is growth or decay, but the B value, because I had to flip that fraction, 5/3 is actually greater than 1, which makes it a growth factor. So this would be a growth function. So hopefully you can understand the difference between the two. You basically just have to see, is it a growth factor or a decay factor based off of that B value being greater than 1 or less than 1. And of course, you have to make sure you're checking those A values to make sure that they're always positive. So the basic shape of an exponential decay function is going to be decreasing. So we knew growth, I showed you at the top of the notes, it was kind of starting out with like a level line almost and then going up, but the decay function just goes down. But notice there's still, neither one of them is on underneath. It's still kind of going to be above that asymptote. So again, when we do this, you can use your graphing calculator and type this in and get your chart off of your calculator. That's always an option. Or you can just kind of plug them in your head and fill it out that way. So if I were to do like 1/2 to the 0 power, we know that's 1. 1/2 to the first power is 1/2. 1/2 to the second power would be actually 1/4. And 1/2 to the third power would be 1/8. Now, if we're doing a negative exponent, right, just to remember our exponent rules, if I were to do 1/2 to the negative 1 power, just like we went over, you would have to flip that fraction, right? So it's really 2 to the first, which is 2. Just like if you were doing 1/2 to the negative 2 power, then you would flip it and you would get the positive 2, and that would make that 4. And then this one here would be 8. And of course, you can get them off your graphing calculator table as well. So now we're going to plot these just to kind of look. So -3, 1, 2, 3, 4, 5, 6, 7, 8. -2, 1, 2, 3, 4. -1 and 2, 0, 1, 1 and 1/2, 2 and 1/4, and then 3 and 1/8. And you can kind of see how the graph starts out with large numbers and then decreases, and then over time it gets very close to that 0. So as x approaches positive infinity, which is the right side of my graph, the y is approaching 0. So that's where it's getting very close to, but it's not going to touch. As x approaches negative infinity, which is the left side of the graph, the y approaches positive infinity. So this is the exact opposite of the exponential graph functions we did yesterday. For those, as we went to the right side of the graph, that's where the y approached positive infinity, and on the left side is where it approached the 0. Okay, so once again, this is your asymptote here, where it's approaching. So my asymptote would be that line y equals 0, which is actually your x-axis for this particular example. Okay, so just to recall some of the things from yesterday, like I mentioned, a lot of what we're going to do today is similar or the same as what we did yesterday. So it's just a couple slight changes, but that's okay because you want to be able to recognize the difference. So again, the characteristics of the graph, y equals a times b to the x power, and I like to put that b in parentheses, just so I remember that the exponent always comes before the multiplication there with PEMDAS or order of operations. With the parent function that does not have an h or a k that we looked at yesterday, the point 0a will be the y-intercept. The x-axis, it will be the asymptote, so we just went over that, so that would just be the y equals. The domain is still all real numbers, and the range is still the same as yesterday. So if your a value is positive, your range is y is greater than whatever that asymptote is. If your a value is a negative, so not exponential decay, but one of those other versions, then your y's will all be less than the asymptote value. Or in this case, with the parent function, that would be a 0, but as you adjust for different, different exponential functions that I've manipulated a little bit with the h and the k. So identifying the y-intercept, the asymptote, the domain, and the range. So just as a little refresher from yesterday, because it's not on here yet, is if you remember, this is our initial function, right? But then we have b, and then x minus h, and then the plus k at the end. So if we're doing the y-intercept, that is simply going to be whatever you get when you plug the 0 in for x. Now, if you just have a parent function where the h and the k are both 0, then it's going to be your a value. But in this case, we have this -2 here. So if I raise 1/3 to 0, I get 1, and then 1 minus 2 is -1. So that's my y-intercept. Now, the asymptote is always y equals that k value, and this k value is -2, so it'll be y equals -2. Your domain will always be all real numbers, so I'm going to do that little fancy R. And then my range is the same thing as the asymptote, but with an inequality sign, and your inequality sign is just going to be a greater than if your a is positive, and y is less than if your a is negative. This a is a +1, so its y is greater than -2. So same thing as yesterday. None of that's any different. Okay, so the y-intercept for number 2, we're plugging in the 0 for x and seeing what we get for y. So when I put a 0 in here for x, I have a -1. That would make sure I'd have to change my 1/5 to 5 to the first power, which is just 5, and 5 times 2 would be 10. So my y-intercept would be 0, 10. And you can also get this on your graphing calculator if you're not sure or you want to check. It's not necessary, but you can. The asymptote is y equals 0 in this case because there's no k value adding or subtracting at the end. Then our domain is always 100% of the time for these graphs, all real numbers. And the range will be y is greater than 0 because our a value is positive and our asymptote was y equals 0. And then our third one, so our y-intercept is 0, comma. So if I put a 0 in here, the 2 goes to a 1, right? Because 2 raised to 0 is 1. Even if you switched that to 1/2 to make that a positive, it would be 1/2 raised to 0, which is still 1. 1 times -4 is -4, and -4 plus 3 is -1. So that's your y-intercept. The asymptote is y equals 3 because that's our k value. The domain is all real numbers, and the range is y is less than 3 because our a value is negative. Okay, so that's a lot of review from yesterday. So now as far as graphing these functions, just like I did yesterday, I'm going to graph that parent function, and we're still going to use that shifting that we talked about yesterday to do the actual graph. So now this one is just a parent function here. There's no h and k, so I'm not going to have to worry about any shifting here. So I'm simply just going to get my table of values, whether you want to do that on the calculator or you want to do that just like in your head, which is what I'm about to do. So I typically do -2, -1, 0, 1, and 2. If I put this raised to 0, since there's no h and k, that y-intercept is just going to be 0, 3. If I raised it to the first power, that would be 1/4 times 3, which is 3/4. If I raise it to the second power, that would be 1/16, so I would have 3/16. Now, if this was a -1, that would be 4, and 4 times 3 is 12. And if it was a -2, it's some number that's going to be off the graph. So I think that would be, 48. All right, so that's not going to fit on the graph anyway. Either of those are. So I'm starting with 0, 3, 1 and 3/4, 2 and 3/16. And this is my graph. Like I said, there's no shifting for this one, so we don't have to worry about shifting left or right or up or down because the h and the k are not there. They're both 0. Okay, so number 2 is also just a parent function. However, this time, my a value is -2. So this is not growth or decay. We could see the first example was decay, right? So this one is actually neither. And that's because it's going to look like a decay function, but it's going to be reflected over that x-axis. So when I go to make my points, you could do the points without the negative and then reflect it, but that would just be more work. So we're just going to make a table of values, and we're going to put in, the basic 5 numbers there. So when I put in a 0, 1/3 to 0 is 1. 1 times -2 is -2. If I put in, let's see, a 1, I would have -2/3. If I put in a 2, I would have, let's see, -2/9. If I put in a -1, that flips that to 3, and I get -6. And if I put in a -2, I would get -18. Okay, so -1 and -6 fits. 0, -2, 1, -2/3, and 2, -2/9. And you can see that that asymptote is still y equals 0 because the k value is 0, just like the last one. Okay, so now the third one, we have that h and that k, so this one's going to require a little shifting. So I'm just going to graph my parent function, which is highlighted here, and then I'm going to shift it according to the h and the k. So my a value is +5, and this b value is less than 1, so this will be a decay function. Now my h is -3. Remember, the sign's always opposite on the h. The k value is -2. So after we do the parent function, we're going to shift it 3 to the left and 2 down. So for my parent function, since it's a lot easier to do that in your head than doing the whole big thing in your head. If I put a 0 in here, I would get 5. If I put a 1 in, I would get 5/8. And if I put a 2 in there, I get 5/64. If I put a -1 in there, that flips my 1/8 and I get 40. And then I'm not even going to bother with the 2. It's going to be a gigantic number. So -140 is off the graph. 0, 1, 2, 3, 4, 5, 1 and 5/8, 2 and whatever. So this is my parent function with the black dotted line here. Now, if I want to do the actual function, I'm going to shift these points. -3 was my h, so 3 to the left, and then 2 down. So 1, 2, 3, and then 2 down. 1, 2, 3, and then 2 down. 1, 2, 3, and then 2 down. And there you go. And you can see now that the asymptote, where the graph is kind of leveling off, is that -2 value there. But all the numbers are above it. Okay, so going on to the next page, we're going to do the same thing with these graphs, but we're also going to review filling in that information as far as the y-intercept, the domain, the range, the asymptote. We didn't do that too much on the first 3, just to kind of review how to graph, but we're going to kind of review that a little bit more now. Okay, so again, I'm going to highlight the parent function. This one is just a parent function. There is no h and k. So we know the a value is +6. The h value is 0, and the k value is 0. So the b right here is less than 1, so we know that this is a decay function. So now I'm going to go down and fill in my information at the bottom here. So the y-intercept, we'll do that last. So the domain is always all real numbers. My asymptote here is y equals 0 because my k value is 0. And then my range is going to be y is greater than 0 because the k value is 0 and our a value is positive. Now the y-intercept, since this is a parent function, there's no h and k, it's just going to be 0, whatever my a value is. We don't have to do much math for that one. But if you were doing, an h or a k that are different, then that's going to require a little bit more work. Okay, so now as far as plotting this, we know we have the 0, 6. All right, and then we want to try to fit one on each side. 1, 2. So I'm going to try doing, let's say I do a 1. That's going to be 3, so 1, 3. If I want to do 2, 1/2 to the second power is 1/4. 1/4 of 6. 6/4 is 3/2, or 1.5. So right there. And then if you want to try -1, that would flip your 2 and you'd have 12. That's going to be off the graph. So it's going to look something like that. Okay. All right, so now going on to the next one. Again, we just have a parent function here. The h and the k are both 0, right? So the a value is positive. The h and the k are both 0, so we don't have to worry about any shifting. And because the b value is less than 1, we know that this is a decay function. So now to go down to the bottom, the y-intercept then will be 0, 4. Since there's no h and k, the domain is always all real numbers. The asymptote is y equals 0, because that's the k value, and the range will be y is greater than 0. So now we know we have 0, 4, but we probably want to get a couple more points, right? So I know I have my 0, 4. If I put in a 1, 3/4 to the first power is 3/4 times 4 will just give me 3. If I put in a 2, I would have 9/16 times 4, which ends up being, I believe, 9/4, or 2.25. So 1, 3, 2 and 2.25. And then if I did a negative one, that would give me, I believe it's like 5 1/3. So that'll be right around there. So this one's kind of, oops, drew that a little crooked. So it's kind of going to go like that. Now we do know the asymptote's 0, so that's how we know it's going to slope down at least until we get to that x-axis, but it's just like a longer slope there. Okay, now the next one, before I figure out my parent function, I've got to get rid of this negative x. That's just not going to be something that we can work with there. So first I'm going to do is rewrite this to y equals -5 times 1/2 raised to the x. Okay, so now I can graph that. With the negative x there, you've got to get rid of that first. So now my a value is negative this time. So it's not growth or decay. It's just one of these other types of exponential functions. And then the h and the k are both 0. So as far as your y-intercept, that's not going to be any different. It's just going to be the 0 and the -5. Your domain is still going to be all real numbers. Your asymptote is going to be y equals 0, but this time your range is going to be y is less than 0 because this graph is going to be reflected over the x-axis. So if I were to go graph my points, I have 0 and -5. And I'm going to do my little table to get a few more points here. So if I put in, let's say, a 1 there, I would have -5/2, or -2.5. If I were to put in a -1, that would flip that to 2. I'd have -10. So I don't know if I can fit that. That's going to be way down here. So you know it's going to be something like that. All right, so hopefully that gives you the idea of how to just do the basic decay functions, what they kind of look like. They're doing the opposite direction of what we did yesterday. But most of the information is still the same, finding the y-intercept, the domain, the range, the asymptote, very similar to what we did yesterday. So now when we move to these ones on the bottom here where there's the shifting, again, very little is going to be different than yesterday. So my parent function is just the a times the b raised to the x, right? So here, we know that my a value is 8. The b value is less than 1, so this is decay, of course. My h is -2. Remember, the h is always the opposite sign, and then the k is the -1. So if I want to go fill in this information down here at the bottom, we know that since the h is -2, it's going to shift 2 to the left. Since the k is -1, it's going to shift 1 down. The domain, all real numbers. The asymptote is y equals -1, since that's my k value. And then the range is y is greater than -1 because the a value is positive. So now the y-intercept, this time we actually have to plug that 0 in and work it all out, or you can type the whole thing in onto your graphing calculator and get your table values from there. So for me, I'm just going to make my table here. Whether you're getting it off the calculator or doing it in your head, that's completely up to you. So if I put my 0 in for x, okay, I would actually, so then I have 1/4 to the second power, which is 1/16, times 8 is 1/2. 1/2 minus 1 is -1/2. Now, remember, you can graph this straight away if you're using a graphing calculator, but I'm going to do the parent function and then shift it, because putting it into this big, long equation, all these numbers will be a little bit more tedious for me. So I'm graphing my parent function over here, and then I'm going to shift that. So if I'm just doing my parent function, this is 0, 8. If I put in the 1, then I would have 1, 2. If I put in a 2, then I would have 1/2. If I put in a -1, that's 2. And if I put in a -2, let's see, -2, 4 to 16, that would be a really big number, I think. Okay, so -1 and 2. 0 and 1, 2, 3, 4, 5, 6, 7, 8. 1. Wait a second, I messed something up here. So if I put in a -1, oh yeah, that's 32. I'm sorry. So I'll be way off the graph. Then we have 1, 2, and 2.5. So this would be my parent function here. Now, if I want to shift this, I'm going to shift all of the points that I have on here, 2 to the left and 1 down. So 2 to the left and 1 down, 2 to the left and 1 down, 2 to the left and 1 down. And that would make sense because the asymptote is supposed to be -1, so that's kind of where it's leveling out. Okay, so let's take a look at number 5. So this is my parent function right here. So my A value is just +1. The B value is less than 1, which means this is also decay. The H value is +1. The K value is +4. So filling in the bottom, I have shifting 1 to the right for that +1 H value. I'm shifting 4 up for my K value. My domain is all real numbers. My asymptote is y equals 4, and my range will be y is greater than 4. The y-intercept will be what we get when we put 0 in for x and work out that whole equation. So when I do my parent function, I'm just doing the highlighted part. If I put in a 0 there, I get 1. If I put in, let's say, a 1 there, I would get 1/3. If I put in a 2, I get 1/9. If I put in a -1, I get 3. And if I put in a -2, I get 9. So -2 and 9 is off my graph. -1 and 3, 0, 1, 1 and 1/3, 2 and 1/9. So it's going to be kind of like this. That's my parent function. Sorry, it's very ugly. Okay, so now to do my shifting, each of these points will shift 1 to the right and 4 up, 1 to the right, 1, 2, 3, 4 up, 1 to the right and 1, 2, 3, 4 up, 1 to the right, 1, 2, 3, 4 up, and then 1 to the right and 1, 2, 3, 4 up right there. So this is what you'll end up with. Okay, now it just so happened that my y-intercept is visible to me on the graph. It is 0, 1, 2, 3, 4, 5, 6, 7. So I can go ahead and fill that in. If that was not something visible to me, like it was off the graph or something, I would just have to do the calculation or look it up on my table on my calculator. All right, so we've got one more of these. My parent function is right here, highlighted. My A value is a negative, which means this is a neither decay or growth function. My B value is less than 1, but doesn't matter. It's not growth or decay right now. But we do know it'll be a reflection of a decay over the x-axis. My H is -3, and my K value is 2. So filling in all that information on the bottom, since my H is -3, I'm going to shift 3 to the left. Since my K value is, 4? No, 2, sorry, was 2. I'm going to do 2 up. Domain is all real numbers. Asymptote is y equals 2, and the range will be y is less than 2 because that A value is negative. My y-intercept will be 0, whatever. Okay, so to do the parent function first, if I put in 0, I get -9. If I put in a 1, I get -6, I believe. If I put in a 2, I get -4. If I put in a -1, let's see, do I have that on my paper? I think it's a decimal, -17.5, if I can read my paper correctly. And that's all I'm going to do. All right, so that's off the graph anyway. 0, -9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 and -6. 2 and -4. And then this would be my parent function kind of going like that, right? Now, if we shift all of these, we're going to shift them all left 3 and up 2, correct? So I'm going to go to the left, 1, 2, 3, up 2, to the left, 1, 2, 3, up 2, and to the left, 1, 2, 3, up 2. And this is what my actual function will look like. Now, it's kind of hard to see where it's crossing on the y-axis. It looks like it's in between 0 and -1, but you might want to just put that in on your calculator to see. So if I go to my calculator here and I type in -9 parenthesis 2 divided by 3 parenthesis, and then I'm going to raise that to, if I put a 0 in, it will just be a 3. And then I have, what's at the end, -2. And I get, wait a second, did I type something wrong there? I can't read my other page. Oh, it's a +2, that's why. Okay. All right, so -9 times 2/3 raised to 3. Oh, shoot. Raised to 3 plus 2. All right, so -0.66 repeating, or -2/3. So preferably give me the answer as a fraction rather than a repeating decimal, and there you go. Okay, so the last thing we have to do to finish up this decay is very similar to what we did yesterday, of course, but it's just a decay model instead of a growth. So yesterday we talked about exponential growth, and the only difference was this b value. So if you remember, the formula we've been using is a times b to the x, and that's the same for growth or decay. But remember, if the b is greater than 1, that's a growth factor. If if the b value is less than 1 but still greater than 0, then it's a decay factor. And how would you get a growth factor or a decay factor? Well, obviously, if you're adding a percentage or a decimal to the 1, it's going to be a greater than 1 number, which gives you a growth factor. But if you're doing 1 minus the decimal, you'll have a number that's less than 1, which will make it a decay factor. So that's really why there's a minus for the decay problem and a plus for the growth. But the actual information is still the same. So A is still that initial amount you're starting with. R is still the percent, but it's expressed as a decimal just like it was yesterday. And now we're going to subtract it from 1 and call it a decay factor instead of adding it to 1 and calling it a growth factor. So for example, a new car costs $2,300. That's an initial principal amount. The value decreases by 15%. So the model would be y equals 23,000 times 1 minus 0.15 raised to t. Now, to get that decay factor, you're going to go ahead and do that subtraction, and 1 minus 0.15 is 0.85, and now you can see that this is a decay function because that number in there is less than 1. So now we can use this model to find the value after 3 years. So 2 ways you can do that. The first way, you can just simply enter it in a calculator like you would normally. So 23,000 times 0.85, and you can raise it to how many years, which in this case is 3. So you get 14,124 and then 88 cents. But remember, if you wanted to find more years out, you could then analyze the graph to predict when the value will be half of the original. So this is where you'd want to use your graphing calculator. So if you go into your y equals and you type in your 23,000, and then you have your 0.85, and you're just going to make sure you raise it to the x or the t. So if you look at my calculator button there in red, it says x comma t. That's because that's the variable you'd use for the time there as well. So now if you look at the graph, we're only going to be concerned with this first quadrant here. So it might be hard to see it because we have these large, if you look at your y equals, it's starting at 23,000. So right now that's way off the graph and we're not seeing it. So you could adjust your window to see it, or you can really just look at your table. So if you go to your table you know that at year, where are we? So it started at $23,000 initially at year 0. Right now, time doesn't go backwards, so we're only concerned about these positive values for x because they represent years. So half of 23,000 is what? 11,500. So after how many years was it about half? So you'd say probably like maybe 4.5 years, or something like that, because between 4 and 5 years, it went from 12,000 and it dropped down to 10,000. So somewhere in that 4 to 5 year range is when. So you'd say, predict when the value will be half the original, and you might say like between 4 and 5 years. Okay. All right, so let's do the next one. So you buy a new computer for $21,100. The value of the computer depreciates, so that means it's losing value at 28% each year. So write the model. So y equals 2,100. Now this is decay, so you're going to do 1 minus 0.28 because it's losing that value. So how much is it retaining? Well, it's going to retain 1 minus 0.28, which is 0.72. So it's retaining 70% of its value each year. So this is the model. The model still has a variable for the number of years because the model should be something you can use for any number of years. So now it says use the model to estimate after t years. So that's when we're going to plug in a 6 there. And you would do that on your calculator. And you should get $292.56. Now, then it says estimate when it will have a value of 40. And you don't want to keep guessing and checking y values of 40. So this is where you really want to use that graphing calculator feature. So you go to your y equals, you're going to type in the 2,100 times 0.72. Make sure you're raising it to the variable x or t. If you put a number there, it's not going to do anything but graph a flat line because it'll only graph that 1 year. Now you're going to go to your table and you want to see when will it have a value of $40. So again, starting at 0, that's the initial amount when you purchase the item. Just use your arrow keys to go through the years until it's worth about $40. So in about 12 years, you can see that the value is about $40. So 12 years. All right. So I think that we have just completed our notes on exponential decay. As you could see, a lot of it was pretty much the same as the growth with a couple slight subtle changes. Make sure you know those changes because those are important questions when we'll ask like, what's the difference between the two and things like that. And if you have any questions, don't be afraid to reach out, ask for help, remind, email, whatever method works for you. And I hope you enjoy the rest of your day. Thanks.